Good morning. The previous recording was not a very good one, so I decided to repeat these hard problems today and then continue to the last session for mathematical induction. I will try to explain it from a different perspective. Might be it is easier for you to understand the problem. So the problem is this, yes? So we want to show that using, of course, mathematical induction, it hasn't mentioned that you have to use mathematical induction. But this is the topic on mathematical induction, so we're probably supposed to use mathematical induction to prove this. We want to prove that this expression on the left, where n is an integer greater than or equal to 1, which means it is a natural number, we want to prove that the left-hand side equals to the right-hand side. Okay? Okay. So we want to use mathematical induction to prove this equality. So might be that would be easier if I try to describe this for you in this way. First of all, if you don't mind, instead of 2n at the end, I clean it and write n plus n. Yes, because n plus n is the same as 2n. But what is the benefit of writing it in this form? Because then you can understand the meaning of these dots better. Yes, because it means that you see this n is in common to all of these fractions here. But the first term starts with 1, the second term starts with 2, and it means that if you continue this pattern, you eventually reach to n again. So when I give you an n, you put the same n. For example, if I give you 5, then you put 5 here, up to 5 here. But the first term becomes 5 plus 1, the second term becomes 5 plus 2, and then you continue until you reach to 5 plus 5. Yes? So that's the meaning of it. And I would say that if I want to write it a little bit more compactly, to prevent not writing so much to get disturbed, I would say that if you don't mind, let me call the left-hand side an, to simply write it. It is something depending on n. I will call it a sub n, and then I would call this one b sub n. Yes? Okay, we want to prove that. Okay, so we want to prove that an is equal to bn for all choices of n. But the point is that instead of proving that an is equal to bn, okay, so we want to prove that an is equal to bn. But do you agree that instead of proving that an is equal to bn, because you remember we solved this problem once, there were some technicalities going on, I would say that it would be easier to prove that an minus bn is equal to 0. I want to prove that an is equal to bn, but this means an minus bn is equal to 0. So if I succeed to show that an minus bn is 0, then I am done. Because my goal is to show that an is equal to bn. If I can show that an minus bn is 0, then I am done. So if you don't mind, you see it is easier to write it in that way. I was thinking about it. So if I take this pn, my goal is to show that this is true. Okay, how can I do that? The first thing I have to do is to calculate to see if P1 is true or false. So P1 means what? I replace n everywhere with 1. Becomes 0, but still it is a question mark. I have to confirm that a1 minus b1 is indeed 0. So this means that this itself is equivalent. But what is a1? A1 means go here and replace n with 1. When I replace n with 1, on the left-hand side, I only get the first term. So this becomes a 1 over 1 times 2 minus. When I say b1, what is b1? It means that I also get the first term, but for n equals to 1, which is what? 1 over 1 plus 1. First tell me, do you understand that this is a1 and this is b1? Yes? Okay, then I have to confirm that this is indeed 0. Is it true or false? Yes. It is true, because this is 1/2, so it is true. Now I assume that P of k is true. Okay, P of k means I go here and replace n with k everywhere. So this becomes ak minus bk is equal to 0. This is assumed to be true. What is the goal? The goal is to show that P of k plus 1 is also true. But what is pk plus 1? It means go here, replace n with k plus 1 everywhere. This is to be proven, yes? So this is just mathematical induction. But if I want to use my assumption, I have to write this in a way that I can somehow use this fact. Because when I write it in that form, I do not see AK and BK in this expression so that I can use it. So my goal would be to write this in a way that this becomes transparent in it. Okay? Okay, so let us see what happens. If you want, I can write this once. So what I will start from the left-hand side here, which is a sub k plus 1 minus b sub k plus 1. Okay, let me write something in front of it. Okay, can you tell me what can I write for a sub k plus 1? This is my an. A sub k plus 1 means go here and replace every appearance of n with k plus 1. So let us just do that. So what happens? This becomes 1 over 1 times 2 plus 1 over 3 times 4. And this will continue until I replace n with k plus 1. So let us do this in our head somehow. If I replace n with k plus 1, this one becomes 2, k plus 1 minus 1. When you simplify that, it becomes 2k plus 2 minus 1 is 2k plus 1. Yes? So then it becomes 2k plus 1 here. What happens for the next one? The next one becomes 2, but instead of n, I put k plus 1 again. So this is a sub k plus 1. But can you tell me what is the previous term, because that is important? What is the previous term? So you see, the first number on the left goes 2 steps at a time. It was 1, it is 3, the next one is 5, and etc., etc. So if you want to go back and find the previous term, you have to subtract 2 units at a time to go to the previous one. So if the first number appearing here is this number, what is the previous one? Can you tell me? What is the previous one here? Because here I also have 2 numbers. One number sitting here for the first term, and one number sitting here for the second factor. So what is the number that I have to put here? 2k minus 1. 2 units less than this, which is 2k minus 1. Yes? Okay, now can you tell me what this one is? What is the next number here? Again, here you see it is 2, this is 4, the next one is 6, so you are going again 2 steps at a time. 2k, because what is this number, by the way? This number is 2k plus 1, which is 2k plus 2. So it means the previous one corresponding to this one is 2 units less. So it is 2k. Yes? So this is a sub k plus 1. So let me write it like this. Minus, this is a little bit tricky, I want you to understand. So what is minus b sub k plus 1? When I say b sub k plus 1, it means you have to replace every appearance of n with k plus 1 in this side. So if I change this to k plus 1, it becomes k plus 1 plus 1. I am replacing n with k plus 1 everywhere. The next one becomes what? K plus 1 plus 2. And it continues until the very last. Let me write it here. I think this is not confusing at all. What I am doing, I am just replacing every appearance of n with k plus 1. Is that clear? I took these n's here everywhere. Even here I have two n's. I took them and put k plus 1 instead. Okay, is that clear? Okay, now I want you to guess what is the previous one and what is previous to that. The reason that I am trying to write the previous terms, because as I told you, my goal is to make this appear so that I can use it. Now, try to answer this question. So definitely the numerator is not something hard. It is what? What is the denominators? 1 here and 1 here. Okay, what is the previous one? And in this case, you see I need this one as well. What is the previous to that one as well? So can you tell me? Look at these dots, k plus 1, k plus 1, k plus 1. And then here I have 1, I have 2. What is coming next? 3, 4, and I have reached to k plus 1. So what is the previous one?
K plus 1 plus k.
K plus 1 is common to all of them, but the previous one has 1 unit less than this. Yes? And what is the previous to that?
K plus 1 plus k minus 1.
Yes. This is understandable. Do you understand what's going on? So of course, the reason that I am trying to write these, as I told you, because I want to somehow be able to use this assumption. I will tell you how this will help you now. Okay, so if you don't mind, let me simplify them here with a different color. So this is what, instead of this one, what can I write? There is a better name for that. This is k plus 2. Yes? And if I ask you what is this? This is 1 over k plus 3. Now let me continue this list. What is this one?
2k.
2k, but let me write it as k plus k. That's 2k. Okay? And then what is this one? Let me write it as 1 over 2k plus 1. And notice this one finally, 1 over 2 times k plus 1. So these are the terms, yes? Understandable? Okay. Now let us go to the next line. One thing that I want to do, if I ask you what can I write for this part, can you tell me what can I write for this part? What is that? Look here, this is an. So what is that part? What is the difference between this and that? They are identical. The only difference is that instead of n, I have k. So if this is an, that is a k. So that is ak, agree? So this is just ak. And then I copy and paste the rest of it. But if you don't mind, let me write 2 instead of being in the middle. Let me start with 2, and then I have 2k plus 1 and k plus 1. Why this is good? Because I told you my goal is to somehow make AK and BK in my expression so that I can use this fact. Any questions so far? Okay, now this one I want to ask, what can I write? If I ask you what is BK, it starts from 1 over k plus 1, 1 over k plus 2, until 1 over k plus k. Yes? So if I ask you what can I write instead of this, can you tell me what can I write instead of this part? What can I write about this part? It is 1 over k plus 2, 1 over k plus 3, up to 1 over k plus k, which is not exactly bk. Do you agree? Because when I say bk, it starts with 1 over k plus 1, then continue until 1 over k plus k.
Is it then bk plus 1 over k plus 1?
No, a small flaw. Can you fix this? So he said bk plus 1 over k plus 1. It's a small mistake there. Yes?
It's supposed to be
Minus. Yes, because bk it starts from 1 over k plus 1 and then 1 over k plus 2 up to 1 over k plus k.
Yeah.
This is bk. But you don't have the first term. So it is not bk, it is bk minus the first term. Is that clear? Everyone clear? So if I ask you what is this expression is just bk, but this is not bk because it is missing its first term. So it is bk minus its first term. Clear? Okay, and then I copy and paste the rest. The rest means this. So I would write plus 1 over 2k plus 1 and plus 1 over 2 times k plus 1. Oh, sorry, I made also another mistake. This sign is negative. I don't know why I put positive here. Yes, is that clear? Because this was negative. I mistakenly wrote positive. Okay, just I want to wait. Is that understandable what I'm doing? Yes? Okay, now you see I can now somehow use this assumption. Why? Because I can reorder them a little bit. What I do, I will take AK that appears here. Remember, this minus sign goes here, 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 and there. So if the minus sign goes here, it becomes minus BK, and I put it next to AK. I want to rearrange them a little bit efficiently. Okay, and then the rest of it is what? This is left. Remember, this minus sign also goes here, so this becomes plus. This minus sign here and there will change them, yes? Yes? Okay, so what I do now, I simplify. Can I use the assumption in my mathematical induction now? Yes? Because if I ask you, do you know something about this? What is the answer?
It is 0.
It is 0 because it is assumed to be true. Yes, so this part is now equal to 0. So I need to, this becomes equal to, this part is 0 by assumption. This is left for me to calculate. So I will take the common denominator. What is the common denominator here? 2 times 2k plus 1 times k plus 1. This one has not changed at all with respect to this, so I am not rescaling the first fraction, so I have to write 1 on top. But if you compare this one with the denominator in the second one, what is left is 2 times 2k plus 1. I multiply the numerator of that fraction by this, but it is plus, this one is 4k plus 2. Okay? And then compare this one with the denominator of the third one. First of all, there is a negative sign here. And if you compare them, this is gone. 2k plus 1 is left, which is 2k plus 2. But because of the minus sign, it becomes 2k minus 2. Yes? And if you compare this finally with the very last one, 2 and k plus 1 are there. So I have to rescale it only by this factor. But there is a minus sign there, so it becomes minus 2k minus 1. Okay, and then try to see what happens. 2k minus 4k gone. 2 and 2 are gone. 1 and 1 are gone, so it is 0 over the same denominator. But that 0 over the denominator is 0, and that is finally equal to the right hand side. That is exactly what I did before, but probably a little bit disorganized. So I think now hopefully you understand what is the picture. Is that clear? But still, I would consider this higher than the level of the other questions in the book. Is that clear? Yes.
Would something like this come on the test? Or is this too high level?
No, it is in your book. Yes?
Yeah.
But don't ask these questions. I'm not very good in that. But don't worry about this. You have seen my exams, yes? Okay, so let me also go to the next problem, the geometry one. Then I will come, the trigonometry one. Then I will come back to the geometry one again. So the next problem here that I wanted to show, and I will try to prove a formula later for you so that we can do it easier. So we want to show that cosine x plus cosine 3x, cosine 5x, up to cosine 2n minus x is equal to sine. This 2nx is the argument for sine, is the angle in front of sine, divided by 2 sine x. Of course, this is also a little bit different from the problems we had so far because we have two variables involved in this problem, yes? In all the cases, we had only n in our problem, but here we also have n, we have n and x. Of course, x is an arbitrary number. You know that induction can only be done on natural numbers, so the induction should be done on n, not on x, of course. So we want to show that if we add up these cosines, this can be written much more compactly like this. Okay, so we want to prove this. Okay, so let me just write it here and then try to solve that problem here. So we want to prove that cosine x plus cosine 3x plus up to cosine 2n minus 1x is equal to sine 2nx divided by 2 sine x. We want to prove this. I hope the pattern is clear, yes? Because 2n minus 1 means an odd number. If I put n equals to 1, of course it will generate the first term. If I put 2, 2 times 2, 4, minus 1, 3, cosine 3x is the second term, and this will continue. Okay, so we want to prove this. As before, let me call this Pn, and then I write P1 first and try to see if this is true or false. P1 means cosine x on the left-hand side is the only term that survives if n is 1. On the right-hand side, if I replace n with 1, 2 times 1 times x is 2x. So this becomes sine 2x divided by 2 sine x. This is still not clear if it is true or false, so I have to do it. In this case, I start from the right-hand side. So I would say the right-hand side of the P1 statement is equal to. We have a formula, double angle formula for sine, so I'll use that. It is 2 sine x cosine x. And then I have 2 sine x in the denominator. So then what happens? This sine x, this 2, and that 2 are gone. So this becomes cosine x, and that is exactly equal to the left-hand side. Yes? So we were able to show that, yes, now I can clean this question mark, and now I am sure that this is true. Okay, now we assume that this is true for P of k. We assume that P of k is true, meaning that cosine x plus cosine 3x up to cosine 2k minus 1x is equal to sine 2kx over 2 sine x. Yes? So assumed to be true. Yes? This is P of k. And then we actually want to prove that P of k plus 1 is also true. But what is P of k plus 1? I have to replace every appearance of n with k plus 1. So this becomes cosine x plus cosine 3x, and then it continues. So let me put a little bit of open space so you have enough experience. Why? I will write the last term. So what is the last term? Can you do it in your head? I replace n with k plus 1. What happens? What happens? I replace n with k plus 1. What happens? Here. P of n is this expression. I want to write P of k plus 1. It means go in Pn, find every appearance of n, and replace those n's with k plus 1. That's the meaning of P of k plus 1. What happens?
It becomes cosine of 2k plus 1.
2k plus 1, yes. So this becomes 2k plus 1 times x.
Yep.
Okay, and the right-hand side, of course, is easy. The right-hand side becomes sine 2. Instead of n, I put k plus 1, x, and then I have 2 sine x. Yes? But by experience we got so far in solving these problems, it is always good to write the previous one as well. So what is the previous one? Can you tell me? You start with 1x, then you add 2x to it, it becomes 3. So it is 1, then it becomes 3. For the next one, it is 5. For the next one, it is 7. So if I give you 7, for example, you know what is the previous one? The previous one is 5. So it means that you subtract 2 units. So if I subtract 2 units from this coefficient, what happens? It becomes 2k minus 1x. Yes? The reason that we write this previous term, because I want to make it transparent so that we can see how can I use my assumption. Okay, this is what I want to prove, to be proven. Okay, so I start from the left-hand side of this expression. The left-hand side of this expression is from here to here. But instead of this, I can write something. What can I write instead of the first part of the left-hand side? Because I can assume that the left-hand side is composed of 2 parts. One this bigger part and one this smaller part. But for the bigger part, I do not have any problems because I have something in my hand. What is that? What is that one? I have it here, yes? From here to here is assumed to be this expression. So I take it off and I put this expression. So this becomes sine 2kx over 2 sine x. And then I have plus cosine 2k plus 1x. Yeah, is that clear? Okay, and then let me, I wanted to avoid using the formulas, but it is easier to prove the formula anyway. So let me take the common denominator. What is the motivation behind taking the common denominator? Because I want to reach to the right-hand side. In the right-hand side, I have one single fraction. But here I have one fraction and an expression. It is not acceptable because I want to have a unique fraction. So this motivates me to take the common denominator. The denominator for this one is 1, so that the common denominator is just 2 sine x. And 2 sine x hasn't been rescaled as far as the first one is concerned, so I just copy and paste its own numerator. Then I have addition. The denominator here is 1, so I have rescaled it by this factor. I also have to rescale its numerator by the same factor. So this becomes 2 sine x cosine 2k plus 1 x. That's it. Okay, so if you compare this with what you want to get, you don't have any problems at all with the denominators, yes? Because the denominator that appears so far is exactly the same denominator that I need in the future. So what I need to do is to try to find a way to convince myself that the numerator of this expression can be written compactly in this very simple form. Okay, so that is the only thing that I want to do. So let me try to give you a little bit different approach. It might be, So you might say that, okay, how should I know this? Because I remember I gave this question in one of my exams, and I wrote the formula as a hint to use this formula. Okay? Okay, the formula is something not very hard. I want you to see, I want to have the combination. Here is sine of an angle multiplied by the cosine of an angle. Of course, the angle in front of sine is x. The angle in front of cosine is 2k plus 1 times x. But forget about that momentarily. Let us try to see what happens if I have sine of u plus v, and if I have sine of u minus v. Do you remember we had a formula for this, we had a formula for that? I just write the formulas. It is sine of the first one, cosine of the second one, plus what? Sine of the second one, cosine of the first one. Here, I also have sine of the first one, cosine of the second one, minus sine of the second one, cosine of the first one. So these are nothing strange. Okay, I agree with you. You might ask, well, how can I find these formulas? How can I know that I have to use those formulas here? But that was the hint I gave you in the exam, so that you follow these steps. So then I add them. So let us see what happens. If I add them, what happens? This will be added to this one. So this becomes sine of u plus v plus sine of u minus v. I am adding them side by side. I will do the same thing on the right hand side, but the good point is that this one and that one are exactly the same. They will cancel out. They are also exactly the same, so they add up. It becomes 2 times sine u cosine v. Yes? So that is the formula that I want to use. What does it tell you? It tells you that if you have 2 times sine of an angle times cosine of another angle, this combination, is equal to the sine of the sum of these two angles plus the sine of the difference of these two angles. Yes, is that clear? So u and v are just arbitrary angles. So this is why I have written it in blue, because probably it's not exactly the part of the problem right now. I want to invent or discover a new formula that will help me to manipulate the second part. In the second part, I realize that I have this combination. I have a 2, I have sine of an angle multiplied by cosine of another angle. Okay? Using this, I was able to find this formula. So first of all, tell me, do you have any problems with the blue lines? Okay. Now, I want to give the role of u to x. I want to give the role of v to 2k plus x. Okay? So this is what I want to do. And I want you to help me to continue. So what should I do? I will continue. Go back to the black line now. From there, I continue. So I copy and paste the denominator. It's 2 times sine x. I copy and paste the first part of the numerator as well. It's sine 2kx. And now, okay, what should I write? For the second part, I want to use this formula, but of course from the right-hand side to its left-hand side, yes? Because this is in the form of the right-hand side. So how can I write it? This is u, this is v, this becomes sine of u plus v. So let me write it. Sine of, what is u? U is x. What is v? V is 2k plus 1x. Yes? And then plus sine of the difference between these two. What is that? X minus 2k plus 1 x. Yes? Is that understandable? Okay, now I want to simplify something here. So you see, I can factor x out here between these two. So what happens? X is left here. If I factor x out, 1 is left here. 2k plus 1 is left from here. Yes? So then, of course, 2k plus 1, I can write it as 2k plus 2. Yes? Okay, so this becomes 2k plus 2x. What about this one? I will do the same thing. I factor x out. 1 is left from here. Minus 2k minus 1 is left from here. Yes? But this 1 and that 1 are cancelled. Minus 2kx is left. Yes? Okay, and then I substitute them. So let me just continue 2 more lines, we are done. So this becomes equal to sine 2kx. Instead of this expression, I write that expression. Okay. Instead of that expression, I put minus 2kx. But do you remember a formula in trigonometry math 4? If I have sine of a negative angle, what will happen for that negative sign if I have it in front of a sine? You remember? Yes?
The sign will become negative.
Yeah, its sign goes out if it is sine.
Yeah.
Yes? So this minus sign that appears here, I can pull it out because that's a sign. This will change this to a negative sign. So this becomes negative sine 2kx. Understandable? And then I copy and paste the denominator, and you see that then the problem is done actually. Why? Because this term with the negative sign cancel the first term. Yes? And then what is left for me is the sine of 2k plus 2x, and then I have divided by 2 sine x. But I am done, yes? Do you see what I'm supposed to reach to? This is the one that I want to reach. This is the right-hand side. But of course, 2 is factored out here. So I also factored this out. So there is a 2 here, there is a 2 here. I factor it out, so this becomes sine 2k plus 1 x divided by 2 sine x. And this is equal to the right-hand side. Is that understandable? So the only technical part I would say, because more or less, if you are not horrified from the problem, if you don't fear from the problem, it is not that hard up to here. Okay? And even taking the common denominator is also not hard. But I agree, might be if you do not have enough experience, you don't know how to manipulate this part. But if the hint is already provided, then I don't think that would be hard. Okay? But then, of course, consider this if there are 3 points, and if you do up to here, you will get 2 points. Okay, so when it comes to exams, you need to think in this way. Okay, any questions here? Understandable? Okay, now if you don't mind, let me go back to the previous problem, which was a geometry problem. So I don't know. This we didn't made any mistakes, anything. So I think we can actually. I mean, the explanation was probably good enough. Might be you were tired, you didn't understand. Let me repeat that again. Okay. So in this problem, we are supposed to show the number of diagonals of an n-gon. N-gon means a shape with n sides, okay? N straight sides. Okay, for example, a triangle is a trigon, yes? Or a quadrilateral is a fourgon, yes? Okay, we have pentagons, hexagons, and etc., etc. We want to prove that the number of diagonals of an n-gon, so if you have n sides, dn in this problem denotes the number of diagonals of an n-gon. We want to show that that is equal to n times n minus 3 divided by 2. Okay, so that is the purpose of this problem. Okay, so how should I solve that one? So dn, let me write here, dn, the number of diagonals of a, let me write convex, I will tell you what do I mean, convex n-gon, not necessarily regular. What do I mean by convex? A shape like this is not convex, okay? Because if I take 2 points inside there and if I connect these two, some part of this line lies outside. This is not a convex shape. But in contrary, for example, a circle or something like this is a convex one, because it doesn't matter which 2 points you choose, whenever you connect them, all the parts of the line segment lies inside. Okay, so we can also have a for example, this is a quadrilateral. This is a convex one, because it doesn't matter which 2 points I choose interior to this. When I connect them, all the lines are lying inside. But for example, if I have this scenario, so this one, this is 1, 2, 3, 4, 5. Of course, this is a pentagon, okay? But this pentagon looks a little bit strange to your eyes. But that is in geometry called also a pentagon. But this is not a convex pentagon, because if I, for example, choose these 2 points and connect them, there are some parts of this lying outside. The notion of diagonal doesn't make sense that much for this case. Yes? When you talk about diagonal, you already mean that I have a convex n-gon, because what is the meaning of a diagonal here? Yes? So this, you can talk about that, but you don't need to be worried about it. So in the book, they haven't mentioned the convex because they think that the only n-gon you consider are the convex ones. Okay, so let me just clean that one. I also want to follow the book. So this becomes n-gon. And then what is the statement? So Pn is this fact. Dn is equal to n times n minus 3 divided by 2. We want to prove the truth of this statement for a natural number n, but of course you know that there are some limitations for the n. N cannot start from 1 in this case, yes? Because it doesn't make sense that I have a 1 gon. I cannot have a 1 gon, I cannot have a 2 gon. The minimum value is a 3 gon, which is a triangle. Yes? So the first thing that I need to check, the base of induction is not P of 1. I have to start with P of 3. Okay, I want to see if this P of 3 is a true statement or a false statement. The first thing that I do, I replace every appearance of n with this number 3, so it becomes d sub 3 equals to 3 times 3 minus 3 divided by 2. So I replace every appearance of n with 3. So this means that d sub 3, if you calculate this number, 3 minus 3 is 0, so the answer is 0. Now, this is claiming that d3 is 0. Is this a true claim or a false one? True one. Because when you say I have 3 sides, it means that I have a triangle. If I ask you how many diagonals are there for a triangle, the number is 0. Yes, it is true.
Baba,
Yes.
what is your definition of a diagonal then?
Now, diagonal means connecting 2 non-adjacent vertices together. So if I have, okay, let me get rid of this. Okay. So if I take this point and connect it to an immediate adjacent one, I will not generate a diagonal, I will generate a side. But if I take this one and connect it to any one which is not immediately adjacent to this one, for example, in this case, I have this and I have these are the only options. If I connect this to this is called a diagonal. Understandable?
Yeah.
And this, if I connect this to this is also a diagonal. But if I ask you, do you have more diagonals passing through this point? No. Because to make a diagonal, you need to make a line segment. For having a line segment, you need to have two endpoints. If I choose this as one endpoint, there are other points that I can choose as endpoints, these points. But for these two, I am not generating a diagonal, I am generating a side, so these are the only two ones that I can choose. Does that understand? That's the meaning of a diagonal. So if you have a triangle, you do not have any diagonals. Why? Because if I choose this, are there non-adjacent vertices to this? No. Both of them are adjacent, so there is no diagonal. Okay, so this is true. Now I assume that P of K is true. So to be honest, if I want to be precise here, because I have some limitations on K, if I want to be very rigorous, I have to say let K be a natural number greater than or equal to 3. We assume that P of K that I chose is true. We prove that P of K plus 1 is also true. And that's the induction. The only difference is that K should be a number greater than or equal to 3, of course. Okay, P of K. What is P of K? If I ask you to write P of K, exactly as before, you go to your Pn, replace every appearance of n with K. So this means that dk is equal to K times K minus 3 divided by 2. Assumed to be true. Yes? So how do you read it in English? This is claiming that if you have a k-gon, the number of diagonals of that k-gon is k times k minus 3 divided by 2. Any k-gon that you have. What we want to prove, the truth of P of K plus 1 as well. How can I prove that? First, I have to rewrite it. I have to write it down. So I replace every appearance of n with K plus 1. So this becomes d sub K plus 1 is equal to K plus 1 instead of n. And instead of n, I put K plus 1, but there is a negative 3 there. So this becomes K minus 2 and then divided by 2 to be proven. Yes? So what I want to prove in English, I want to prove that if I have a k plus 1 gon, a polygon with k plus 1 sides, I want to show that the number of diagonals of that particular k plus 1 gon follows this formula. But I have something in my hand. What do I have in my hand? I already know that if I have a k gon, the number of diagonals follows this formula. Yes, questions? Is that clear? Okay, so I want to prove something about a k plus 1 gon. What is the natural step to start with? Yes, is to draw a k plus 1 gon. If you want to do a geometry problem, you usually draw a figure, yes? Okay, but of course, drawing k plus 1 gone is a little bit problematic because we don't know. Because if I ask you to draw a quadrilateral, you draw it simply. If I ask you to draw a pentagon, you draw it simply. But if I ask you to draw an n gone, of course, you need to get an intuition what is okay. But one thing is clear. If I have a k plus 1 gone, how many vertices do I have in that? In a triangle, I have 3. In a, I don't know, quadrilateral, I have 4 vertices. In a pentagon, I have 5 vertices. So if I have a k plus 1 gone, how many vertices do you expect? K plus 1. So it's better to try to draw something instead of writing A, B, C. It is not very clear how many of them I am using. So I write the first vertex to be A1. I'm trying to imagine a k plus 1 gone, yes? And the next one, A2. And the next one, A3. The next one, A4. And of course, this list will continue. So this dot means that you continue, and then at some point you have to come back. And then, for example, the very last one is what? A sub, the very last one. K plus 1. Of course, before that is, this is a K. Okay? Before that, if you want to write, I mean, this is a K minus 1. Okay? So that is some intuition of what is going to happen. So I draw them with solid lines because they are real here. They are really appearing here, but I don't know. These are some dots going on. And then I also have these. I'm trying to give you a feeling of a k plus 1 gone. Yes? Is that clear?
Yes.
Okay. What I want to do, I want to count the number of diagonals in this picture. Okay. But of course, if I want to start counting them, I don't need mathematical induction. I want to do it in a wise way so that I can somehow maximally use my assumption because this is in my hand. I want to do my best to make everything I need out from here. So what I do, I will think in this way. This is a, for example, if you have a hexagon here, 1, 2, 3, 4, 5, and 6. Okay? It is not hard to see 1, 2, 3, 4, 5. Is that right? Okay. So if I take this and connect it to this one, then my original hexagon is partitioned into 2 parts. One part is a triangle, and the next part is a pentagon. Is that clear? So if I take 2 points which are not adjacent, the adjacent one is this one, but the next one, if I connect these two, I definitely partition my hexagon into 2 parts. One part is definitely a triangle. The other part has 1 edge less. Yes? Why? Because 2 edges are now replaced by 1 single edge. So that is clear. So I will do the same thing here. So if I, for example, if I take A1, I'm just working with A1 and AK. You can work with the other ones. I take A1 and connect it to AK. If I ask you what is the name of this shape, everyone knows that is a triangle. But if I ask you what is the name of the shape to the right of this blue line, what is that?
K-gon.
It's a K-gon. Is that clear? Yes? So here I have a K-gon. Okay, now the point is that if I ask you, forget about this triangle part momentarily. If I ask you, do you know how many diagonals are there for this K-gon? The answer is yes, because of the assumption of the mathematical induction. Okay, so the number of diagonals here on this red part, the number of diagonals that you see here, so I shouldn't probably messed up with this hatching. So let me get rid of them, might be you get confused. But anyway, the diagonals here is what? K times K minus 3 divided by 2. Okay, but don't get confused. My goal was not to count the number of diagonals of a K-gon. My goal was to count the number of diagonals of this bigger shape. But I hope that you agree, every diagonal that I count in my K-gon will also play the role of one diagonal in the bigger picture. Is that clear? So for example, if you consider this diagonal in the K-gon, and now do not look at the blue line, still this serves as a diagonal for the bigger picture. Is that clear? So by this I am trying to convince you whatever I count as a diagonal here should be also considered as a diagonal in the bigger picture. Yes? So this is actually something that I need. So by this one, I was able to count all the diagonals in this a little bit smaller picture. But is this the whole story when it comes to the bigger diagonal? Obviously not. For example, this one, connecting this to this, is it counted in here? No. Is this red line counted here?
No.
No. Yes, because it is not a diagonal of my k-gon. But is it still a diagonal of the bigger one? Yes or no?
Yes.
It is. It is diagonal of the bigger one. So I have to consider this. Do you agree? I have to consider this red line when it comes to the bigger one. So that is the only thing. So it means that I have to add something to this. So how many I have to add? Okay? How many I have to add? This is one of them that I have to add. Yes, because I already considered all these vertices. The only vertex that I didn't consider is a sub k plus 1. So I need to focus here. I don't need to focus on other parts. So this is one of them. Of course, if I connect this to this one, it does not work because this becomes an edge. I want to have a diagonal. So the first thing that I connect is these two. The next one is these two. The next one is these two. Yes? And it continues. And then it comes back here. So these lines that you see here, I have to count them and add them to the previous calculation. But counting these are not hard because how many vertices I have in total? I have k plus 1 vertices. How many vertices are now considered here? A2, A3, A4, up to AK minus 1. So how many of them are there?
What's the k minus 1?
K minus 2. Because I started from 2. Or you can see it in this way. How many vertices are in total? K plus 1. How many vertices I did not use here, here, and there? So I take 3 out of it, it becomes K minus 2. Or you can think in this way. The first one in my list was A2. The second one in my list was A3. And then A4 up to A K minus 1. Yes? And if I ask you how many numbers you see in this list, how many numbers you see?
K minus 1.
No, because it starts from 2.
K minus 2.
K minus 2. Is that clear? I don't know. You need to convince yourself the number of those is K minus 2 in any way that you are more comfortable with. So this becomes K minus 2. Yes? But the point is that this problem is still not done. Why is that? Let us go back to this blue edge, this blue line here. Did I count this blue line here?
No.
No, because it was an edge for my k-gon. I only calculated the diagonals. So I didn't count this blue line before. Did I count it in the new one here?
No.
No, because you see I only counted the red ones. But is it a diagonal still for the bigger one? The answer is yes. So I have to add this by hand. Is that clear? I don't know how to explain more than that, but I hope that it is very clear. Okay, and then I have to convince myself if I add these up, it becomes exactly the predicted number here. So the rest of it is just algebra. The hard part was this one, the argument. But then the rest of it is probably simple if I haven't done any mistakes. So k minus 2 plus 1 is just k minus 1. So let me write it simply, k minus 3 over 2, and then I have plus k minus 1. And what I do, I take the common denominator. This I multiply in, it becomes k squared minus 3k. And then I multiply 2 here, it becomes 2k minus 2. And then of course, minus 3k plus 2k is what? Is minus k minus 2 divided by 2. Either you can multiply this or you can factorize this. Because the factorization of this is also very simple, I prefer to factorize it. I asked myself, I need two integers whose sum is -1 and the product is -2, and it's easy to guess. One of them is +1 and the other one is -2. So this is now confirmed. Yes? Is that clear? Okay, so hopefully now everything is clear. I want to I mean, there are some other problems in the book that are also good. Let me just do them. So let us solve some level 3 problems here. Okay, first I want to focus on one of them. I can leave one of them to you and solve one of them myself. So here, this is number theory. So this is telling you that, okay, you can still use mathematical induction even in the context of number theory. So that I told you, whenever you want to prove a statement which is related to a natural number, and the one powerful method is to think about mathematical induction. Yes? So let us, for example, choose the first one. I can leave the second one to you. I want to prove that 3 divides 2 to the power of 2n minus 1 plus 1 for any natural number n. That's the goal, okay? So let me make it a little bit bigger. Oh, that's too big now. Okay. So we want to actually solve that problem. Let me clean the board. Okay, but I think these are not that hard. This, I would call them standard level. This you will see, even though it is in number theory, you might think that this is a little bit complicated, but it's not. Okay, so problem, we want to prove that 3 divides 2 to the power of 2n, is it 2? Yes, 2n minus 1 plus 1. We want to prove this. So I call this my statement Pn. I'm recording or not? Yes. Yeah, that's good. Okay, so how should I do that first? I have to make myself, I need to convince myself that at least P1 is true. So what is P1? I have to rewrite my statement by replacing every appearance of n with 1. But then this tells me 3 divides 2 to the power of 2 times 1 minus 1 plus 1. Is it true or false? Because if I calculate the right-hand side, what will happen? 2 minus, it is 3. Yes, because 2 times 1 is 2, minus 1 is 1, 2 to the power of 1 is 2, plus 1 is 3. So 3 divides 3. True or false? True. All right, assume that P of k is true. What is P of k? I have to replace every appearance of n with k, so this becomes 3 divides 2 to the power of 2k minus 1 plus 1, assumed to be true. And then we want to prove that P of k plus 1 is also true, but what is pk plus 1? Let us do it in our head. Can you just write the correct form of it? I have to replace n with k plus 1. What will happen? I have to replace this n with k plus 1. To the left-hand side is untouched. So I have a plus 1 here, I have a 2 here, but what will be the exponent?
2k plus 1.
2k plus 1. Is that understandable? Okay. This is my goal. I want to prove that this is true. Okay, so I don't know how much do you remember from number theory now, but this is not hard. By the way, these are not something that you forget, okay? When I say 3 divides this, it means this number is divisible by that. So what is the meaning? It means that there is a number so that when I multiply it by 3, it becomes the right-hand side. So I will start. This is probably one of those exceptions that I start from my assumption, yes? Because this was the nature of number theory problems, if you remember. If I ask you to prove something under one condition, then usually you start from rewriting your condition in equality form and try to manipulate it in a way that you can reach to this one. So I am just changing the form of my I want to get rid of this side, okay? By the way, we can do it in two different ways. I don't know how much do you remember. We can use congruency, modular arithmetic, or we can do it in normal way. So let me just do it in normal way. So this is translated in English to in mathematical symbols is that there is a q in z such that the right hand side, which is 2 to the power of 2k minus 1 plus 1, is equal to 3 times q. Yes, that's the mean. Okay, so that is the meaning of my assumption. But my goal is to prove this one, not that one. So I have to look at it and see how can I use that in an effective way so that I can prove this. I don't know how much do you remember from your previous studies. So you need to get some kind of motivation what to do. Do you remember, for example, can you tell me what would be my next step? I want to do something to this expression, to this equality, so that I can get closer and closer to what I want to prove. But it is very, I don't know, if you haven't forgotten those exercises we did, probably you immediately realize what to do. Look, compare that expression with the expression that I want to reach at. Yes?
Could you put in plus minus 1?
No, because this plus 1 I need.
No, I mean 2 to the power of 2k minus 1 plus 1 minus 1.
But what is the benefit?
You could reorder.
That's a good idea, but instead of doing that, okay, you want to make this 1 somehow appear.
Sure.
But there is a better way to do that. Do you remember? We solved a lot of these problems before. Any ideas? Your idea, yes?
Can you multiply by 2 to the power?
Exactly. So you want to make this one plus 1. So you multiply everything by 2 to the power of 2 plus to the power of 2. So I multiply everything by 2 to the power 2. Of course, momentarily, you will destroy this one that you need. But based on the experience you got there, hopefully you realize that is a minor distraction. So this is 2k minus 1 plus 1. On the right-hand side, I also have to multiply by that. Yes? But that was exactly the motivation. That is not hard. If you have forgotten the experiences you got from those lessons, that might be a little bit surprise again. But this we did before, many of these questions. So then you multiply that. So if I multiply this by that, what happens? This becomes 2 to the power of 2k plus 1. Agree? Because when I multiply these two, the bases are the same. I add the exponents, I get that one. But unfortunately, this I have to change it. 2 to the power of 2 is 4. When I multiply to this 1, apparently I am destroying that 1 because I still need 1. But this is also a minor problem if you haven't forgotten. And these numbers are so small, so if you don't mind, let me multiply them. So that is 12q. Okay, but do you remember what was the next step? Again, I want to make this. I fix this part, I destroy that part, but fixing this part is extremely simple. Yes?
Move 3 to the other side.
To the other side. So I add minus 3 to every side, so to both sides. So this becomes 2 to the power of 2k plus 1. This becomes what? 1. And then this becomes 12q minus 3. But this is more or less done, yes? Because if I rewrite this, this becomes 2 to the power of 2k plus 1 plus 1. On the right-hand side, I factor a 3 out. Then it becomes 4 times q minus 1. This is an integer, do you agree? Because q was an integer, so 4q minus 1 is an integer. So I can call it a capital Q. And this capital Q belongs to z. So what does it mean? It means 2 to the power of 2k plus 1 plus 1 is a multiple of 3. If it is a multiple of 3, then it means 3 also divides that new combination. Yes? That's also. So you see, this I wouldn't say this is a, I mean, if the other problems were level 3 problems, this problem is a level 2 problem. It's not hard. The reason that you might think a little bit hard because that was a very big time before you have studied this, I mean, after you have studied these things. But this is easy. Okay, let me also solve one problem in the book, which is Okay, so this problem in the book is also, it is solved in the book itself. So we want to show this. We want to show that this combination for any natural number, but of course they have mentioned from 0 even. So we start from 0 this time. Is always divisible by 3. So no matter what integer you put in, this combination is always divisible by 3. So let me just write it here on the board. Okay, so we want to prove this. So what should I do? I call it Pn first. And because they have mentioned that 0 is also acceptable, so the base of induction is P of 0 rather than P of 1. So I start with 0. P of 0, I have to replace every appearance of n with 0. And then simplify this a little bit. This is just 3. The 3 divides 3. Is it true or false? True. Now I assume that P of k is true. K to the power of 3 plus 3k squared plus 2k plus 3 assumed to be true. I want to prove that P of k plus 1 is also true. But how should I write P of k plus 1? The algebra is a little bit lengthy here in this problem. So P of k plus 1, every appearance of n should be replaced by k plus 1. But because there are powers involved, so I have to be patient and rewrite them. So this becomes k plus 1 to the power of 3. And then I should write 3 times k plus 1 to power 2. And then I would write 2 times k plus 1. And then plus 3. So to be proven, yes? I want to prove the second one. If I admit the first one is true. Okay, so what is your suggestion here for doing that? Because the main goal is to make something in what you want to prove, write it in a way that you can see your assumption somehow there transparently. Okay, so do you have any suggestions for me here? Because this is algebraically a little bit involved. I would myself do it in this way. I will try to simplify this expression, and then instead of thinking about this more complicated expression, I will think about the simplified version of it. Yes? So nobody forced me to start working with this form, so I will try to simplify this here. And then here, there is a formula in formula sheet you rarely use actually, but I want to use it. So the formula, I will write it here. A plus b to power 3 is the first one cubed, 3 times the first one squared times the second one, plus the 3 times the first one times the second one squared, and then finally the second one cubed. So that's the formula in the formula sheet. I use it for here by giving the role of a to k, giving the role of b to 1. So let me just simplify that. So this becomes k to power 3 plus 3 times the first one squared times the second one, plus 3 times the first one times the second one squared, but second one is 1. And then the last one is cubed, which is also 1. Okay. And then here you have to raise it to power 2 and then multiply every term by 3. So let us just do it in one go. When I raise it to power 2, it becomes k squared. When I multiply it by 3, it becomes 3k squared. 2 times the first one times the second one is 2k. I also multiply it by 3 later, so it becomes 6k. And then this one to power 2 is 1. I multiply it by 3 later, it becomes 3. And then I multiply 2 in, so this becomes 2k plus 2 plus 3. And then I will try to simplify this once more. So k3 is alone. But look here, this one and that one are what? I can combine them to 6k squared. Here, this one and that one is how much? Is 11k. Am I right? Yes? And then the numbers are 1, 3, 4, 6, and 9. So if you don't mind, we can replace this in our head with a simplified version of that one. It doesn't matter if I show this or if I show this because they are the same thing. Okay, but now can you help me to do that? This is a little bit tricky. How can I use this fact here? The previous problem was very clear. You just told me not very clear, but it was not that hard. You had experience enough. You told me to multiply by 2 to the power 2. But apparently multiplication is not going to work here. Yes, so what is your suggestion here?
Maybe you group the numbers?
Yes, you need to write this in a way, anyway, you have to do it in a way that you can see this expression somehow in this expression. Otherwise, you cannot use that. Okay, for example, here, k to the power of 3 plus 6 to the power of k squared plus 11k plus 9. This is the right-hand side of this expression. Okay, k3 is good because I also have it here. But 6k squared, I don't want it. How much k squared do I need? 3. So this might motivate you to just keep k to the power of 3. But instead of 3 of them, instead of 6 of them, write 3k squared here. But of course, you cannot throw it away, but you can keep it for the future. Yes, so that is exactly the same 6k squared again. Here I have 11k, but how much k's I need here? 2. So let me just take 2 of them. And then how much is left? 9k is left. I put them there. So still I am writing nearly the same thing. And then how many numbers I need? 3. I have 9, but I need write 3, and then what is left? So if you don't mind, let me write them close to it. Okay, so 3k squared plus 9k plus 6. Yes, is that understandable? So what I did, I simplified the right-hand side because it was too messy for my brain to manipulate it. I simplified that, and then I want to compare it with what I have. That is the motivation. Might be this will not work, then that is a dead end. I have to come back and change my strategy. But fortunately, it works. Can you see that? Why is that? Because according to my assumption, this part is a multiple of 3. Yes? So what can you write for this? You can write it as 3 times q. But this is also multiple of 3, coincidentally. So the problem designed by the person, because you see this is 3, this is 9, this is 6. So I can factor a 3 out here. So if I factor a 3 out here, this becomes k squared plus 3k plus 2. So you have a number which is a multiple of 3. You have another number which is also a multiple of 3. You are adding them. So what can I do? I can again factor a 3 out. Yes? So what can I do? I can factor a 3 out. From here, this is q. From there, it is k squared plus 3k plus 2. Can I call this a capital Q? Yes, because Q is an integer, K is also given to be an integer in the beginning of the problem. So this means that this expression is also a multiple of 3. Okay, what does it mean then? It means this is divisible by 3, or in this new notation, 3 divides that expression, yes? Yes? You can also read the way that they have done it in the book, but that's up to you which one you choose, but both of them are correct. Any questions? Okay, I will go one more session with mathematical induction because there are some problems in the book might be you need explanations. The lesson is of course finished, but you need to practice. And so that's the most important probably, the number theory in this part. The middle one was arithmetic and geometric progression. That's also very simple. But these two topics are actually very important. Any questions? Okay, thank you.